So good afternoon, all of you.
Good afternoon, sir.
Shall we start? I think yesterday we have seen different layers, right? Okay. Now next one. Bandwidth of transmission channel. What is the next topic? Bandwidth of transmission channel. So bandwidth of transmission channel. The first one is coaxial cable. And bandwidth is 750 megahertz. Next, radio wave communication. And its bandwidth is 100 kilohertz to 1 gigahertz. Okay. Next one. Optical fiber. One terahertz to 1000 terahertz. Next one. Microwave or ultraviolet optical fiber more than 100 gigahertz. Okay. Got it? So these are the some transmission channels and their bandwidth. Okay. So coaxial cable having the bandwidth of 750 megahertz. Radio communication 100 kilohertz to gigahertz means through radio wave. Optical fiber is also one transmission channel and its bandwidth is 1 terahertz to 1000 terahertz. Microwave or ultraviolet optical fiber is offering more than 100 gigahertz bandwidth. Okay. Now let's see frequency bands. Some important wireless frequency bands. So first column is for service. Next one is frequency band. And here it is comments. Means this chart will give you clarity which frequency band is for very high frequencies, for television, okay, AM and FM and all these things. So it will give you clarity for that frequency band. So first one is standard AM broadcast. So just I'm writing AM broadcast, and frequency band is 540 to 1600 kilohertz. Okay. Next one, FM. This everyone knows. Even you see 95.0, 93.5, 92.7, all are having range between 88 to 108 megahertz. All the channels are in between this frequency only, not more, not less. Okay. Next one is TV. So you have 54 to 72 megahertz. That is VHF. VHF means very high frequency. Next one, if 76 to 88 megahertz is there, that is television. Next one is 174 to 216 megahertz. This is for ultra high frequency UHF. And again 420 to 890 megahertz is again for TV, that is television. Next one, cellular phone. We are using this in our daily life. Yes, no. Cellular phone. What is the frequency? 896 to 901 megahertz. Mobile to base station. And 840 to 935 megahertz base station to mobile. Last one, satellite communication. $5.925 to 6.425 gigahertz. That is for uplink, and 3.7 to 4.2 gigahertz. That is for downlink. Okay. So these are the some frequency bands used. This is for AM. AM means radio like Vivid Bharati and all. They are using 540 to 1600 kilohertz frequency range. Next is FM. FM we know. Yes. 88 to 108 megahertz. Then this one, that is for TV. You have different frequency bands for TV. That depends on picture quality and all the things. Okay. This is cellular phone. And last one is satellite communication, uplink and downlink. Okay. Note down this. So let's move ahead. Now, let's see the, what we can say, methods of radio wave propagation. Methods of radio wave propagation. Methods of radio wave propagation. Now, how many methods are there? I'm giving you one tree diagram only. See here. First one, ground wave propagation. Next is sky wave propagation. Sky wave propagation. Sky wave propagation. And third one, that is space wave propagation. Sky wave, space wave, and ground wave propagation. What is this ground wave propagation? What happens in this? See point wise. The whatever the radio waves are there, they are moving along the ground. Okay, along the ground. Right. And what happens here, you see, the radio waves are guided along the surface of the earth. Yes. These waves induces charges on the earth and they forms current. So here earth behaves as a leaky capacitor. Yes. And as it is propagating, the wave also loses some energy due to diffraction. And thus ground wave propagation is suitable up to 2 megahertz. Okay. So the drawback is what? This wave propagation, that is ground wave propagation, is suitable up to 2 megahertz frequency. Okay, and as it loses energy, cannot go to long distance. Okay, and one more point for this ground wave propagation is what? Range can be increased. Range can be increased. Yesterday we have learned what is meant by range. Range can be increased by increasing power of the transmitter. Okay, so see first line one more time of this ground wave propagation. These ground wave propagation means obviously these waves are propagating along the ground, and this mode of propagation is suitable up to 2 megahertz frequency. Because it is losing some energy, that's why it is not possible to use it for long distances, and its range can be increased by increasing power of the transmitter. Now this skywave propagation, you see, this skywave propagation is basically with the help of the ionosphere. Okay, with the help of ionosphere, and the range of this frequency, or what we can say, the communication we can do by using this skywave propagation is from 2 megahertz to 30 megahertz. Okay, because this frequency range, in between this frequency, whatever it is there, it will reflect back via ionosphere. Yes, and that's why no need to use anything else. Okay, and here also total internal reflection takes place. That's why whatever the waves you are sending, they may reflect back. Okay, clear through the ionosphere. More than 2 megahertz to 30 megahertz, and total internal reflection takes place. Now here space wave propagation, if you want diagram of this is suppose ionosphere. You see here, this is the ionosphere, and assume that this is the earth. Okay, this is the earth. So whatever you are radiating, this will go like this, and it will reflect back to the earth via this ionosphere. Got it? Radio waves, and this is what? Ionosphere. Next one, that is space wave propagation. See here now, this is line of sight mode, or we can say it as a satellite communication. What is that? Line of sight or satellite communication, and its frequency range is above 40 megahertz. Okay. Now assume that this is what one antenna, transmitting antenna. Okay. And this is again another transmitting antenna. So this line of sight is what this one. So how to find the distance up to which this communication is possible? I will draw one diagram, just wait. This is one antenna, and here also one more antenna is there. Okay. And this one, this is what curvature of Earth. Okay. So this line of sight, you see, straight line. Okay. Now this one is dt. This is height of the transmitting antenna. This side you have one receiving antenna, and this is what HR. So from this to this, you are having DH, DR. Okay, not TH. Why? Because this is R, no, receiving antenna. So that is DR. Now this maximum distance between the two antennas is what? dm, which is equal to dt plus dr, and that is equal to under root of 2r ht plus under root of 2r h into hr. That is for receiving antenna. R is radius of the Earth, and this is what line of sight distance between the two antennas. How you are getting this 2r ht, we will see ahead. Okay, why you are getting this dt is equal to under root 2r h or all these things, we will see ahead. First, you note down this three things, particularly the difference between these three: ground wave propagation, sky wave propagation, and space wave propagation. It is simple, like a boy is playing with ball, or two boys are playing with ball in a room. How one boy can pass the ball to another boy? There are three modes. Either he can pass along the ground, yes. Next way, either he can pass that ball by throwing, yes, without touching the slab. Okay. And third thing, just one, he will throw the ball in such a way that it will incident at particular angle at the slab and it will reach to the person, yes, no, or another boy, we can say. So it is same like that only. Got it? Clear? This is what the difference between this ground wave propagation, sky wave propagation, and space wave propagation. This derivation we will see ahead. Okay. First, note down this. Okay. Now, next one. Relation between range and height of the antenna. Relation between the range and height of the antenna. Now listen carefully. Whatever we got, know that 2RH, 5 we are getting like that, under root. Okay. So let us assume that this is the earth. I am taking little curved part. And this is a tower. Okay. This is height of the antenna, H. And this is what? Radiated wave. This is the radius of earth. Even this is also radius of earth. This point is A. This is B. This is C. And here it is D point. Okay. This is also right angle triangle. And here also this is what? Right angle triangle. And you know this is what? Antenna. What is this? Antenna. Okay, so first of all, I'm taking triangle BCD. Okay, which triangle I'm taking? From triangle BCD. In triangle BCD, this is D, okay? BD is D. BCD, CD square is equal to H square plus D square. Agree with me? Yes, no? This is hypotenuse. H square plus D square. Call this equation number 1. Now, next one. In a triangle, which triangle I am taking now? ACD. I am taking triangle ACD. Where is ACD triangle? This big one. Now this AC square is hypotenuse, or AC is hypotenuse. AC square is equal to AD square plus DC square. AD square plus DC square. So AC square is nothing but R plus H whole square is equal to AD square is what? AD square. AD square is R square plus this is what? CD square or DC square. but as we have taken above CD, so I will write here also CD only. Okay, right? So this is CD square. Here also CD square. So now let's expand this. So a plus b whole square, r square plus 2hr plus h square is equal to r square plus this CD square. Okay. Now we know from one equation CD square is what? Let's substitute from 1. CD square is equal to h square plus d square, and therefore r square plus 2hr plus h square is equal to r square plus h square plus d square. Now this r square cancel, h square cancel, but after transposing means we should transfer this side, then it will become minus and then it will cancel. Okay, so d square is what? 2hr, and that's why we are getting d is equal to under root of 2hr, where this h is height of the antenna, r is the radius of the earth. Understand? Like that we are getting this root 2hr, and that's why the maximum line of sight distance, whatever we got before, that is dm, is equal to under root of 2rht plus root 2rhr. Okay, clear? Understand? Note down. Yes, finished. So let's move ahead now. Now next one, what is the population density? Okay, so first of all, population density. If number of users will increase, no, then there is some problem of signal strength. Yes, no, that's why we are using repeaters. So population density means population per unit area. Population density is what? Population per unit area. Okay, and therefore number of persons covered, therefore number of persons is equal to pi, 2 pi d square into 2 pi d square into 2 pi d square. 2 pi d square into 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 covered population density. And here, what is D? What is D? D is radius of the area covered by single transmitting tower of height HT. Okay, got it. Now, modulation, or first of all, what is the limitation of this particularly ground wave propagation? See here, drawback of ground wave propagation. Next is what? Tell me. Sky wave propagation and space wave propagation. Listen here, very important. Drawback of this ground wave propagation is what? Yes, very good. Yes, Amog. Right. So see here, first of all, this ground wave propagation. In this ground wave propagation, what is the case? Yes, tell me. Already I told. Conduction losses. Yes, no. Conduction losses is the drawback of this ground wave propagation. Sky wave propagation, drawback is what? Penetration of the ionosphere by the high frequencies beyond FC. FC means critical frequency. What is this FC? That also we will see. Okay, critical frequency means same like the maximum frequency allowed, beyond which it will not reflect. Okay, for example, see, assume karo there is a net of fish catching net. So if very big fish is there, this net will break like that. So up to some frequencies, this ionosphere is reflecting back the maximum possible frequency which it can reflect. That is what this FC, and beyond that it will not reflect, it will penetrate. That is what FC means. Clear? Okay, so that is what the drawback. So if suppose we have to use little bit greater frequency for communication, we can't use this sky wave propagation. And next one is space wave propagation. Space wave is what? Limited line of sight. That is what the drawback, and that's why to overcome this we are going for satellite communication. Okay, clear? So this is the drawback of this ground wave, space wave, sky wave, and this space wave propagation. SPWP means space wave and SWP means sky wave propagation. So what is this FC? Let's see. Noted this one? Everyone noted? Please tell me. Note down. Okay, let's move ahead. Now, note point you see, ionosphere behaves as a rarer medium. Ionosphere behaves as a rarer medium by which carrier wave is reflected back. If its frequency f is less than or equal to fc, less than or equal to fc, where fc is called critical frequency and how to calculate this fc is equal to 9 into n max whole power 1 by 2. What is this n max? N max is nothing but electron density, maximum electron density. Okay, this formula you keep it in mind. Okay, noted. Now next one, modulation and its necessity. Modulation and its necessity. First of all, what is a modulation? If dictionary meaning you will see, modulation means change. Okay, if dictionary meaning we will see, then it is what? Just a change. You want previous page, take this. Okay, right. So see here, modulation and its necessity. First of all, what is meant by modulation? As already I told you just now, modulation dictionary meaning means change. But here, what is the modulation? The process of the process of the process of superimposing the process of superimposing low frequency signal with high frequency carrier wave. with high frequency carrier wave is called modulation. Understand? Low frequency signal means, suppose now I am speaking, it is a low frequency signal, and if we are superimposing this signal on high frequency carrier wave, that is what modulation is. Now, why it is necessary? See here, its necessity is what? Number one, to reduce height of antenna, to reduce height of antenna. Okay, see here, if suppose we have a frequency signal, that is, assume that 15 kilohertz signal is there. Okay, how much frequency? 15 kilohertz, and its wavelength lambda, how much you will get rate? How much you will get? Phi is equal to nu lambda, no? Yes, no? So calculate lambda from this. So lambda is equal to what you will get? Tell me. P by nu? Yes, no? P by nu. So that is equal to V is nothing but speed of light or electromagnetic wave. And this is 3 into 10 to the power 8, and frequency is 15 into 10 to the power 3. So this is coming, how much? Check it. 0.2. So this is equal to 2 into 10 to the power 4, and therefore you are getting lambda is equal to 20 into 10 to the power 3 meter. So lambda is equal to 20 kilometer. Okay, this is what wavelength? Yes, 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 no, clear. Now, if I have to, this antenna or whatever the antenna should have, so antenna should have a size, antenna should have size comparable with wavelength, comparable to the wavelength of signal. Now it is possible to make antenna whose height is 20 kilometer? No. So this height is not possible. Understand? Which is not possible. Yes, no? And that's why direct transmission of this type of signal is not practical. Understand? Clear? Yes. This is what your first reason. Understood? Shall I go ahead? Yes. Right. Next reason, that is second number point. To increase the effective power, radiated by an antenna. This is what our second reason. Okay. So power P is dial proportional to L by lambda whole square, where L is what? Length of the antenna. Length of antenna. Understand? So the power radiated for long wavelength baseband signals will be small, but if you modulate the signal with high frequency electromagnetic wave, the effective power radiated will be high. Yes, no? So what we have to do? If frequency is high, your power radiated is also high. Number 3, to avoid mixing up of signals. Okay. If suppose so many signals they are sending without modulation, then there is a high chance of superposition, high chance of superposition. Superposition, you know, है ना? This is because signals from different stations will have nearly the same frequency, but if we modulate the signal from different transmitters using electromagnetic waves, the chance of modulation, chance of superposition can be reduced. And due to modulation, chance of superposition can be avoided. Okay. Clear? This is what the 3 reasons. That's why we are, or that is why there is a necessary of modulation. Modulation means what? Mixing of low frequency signal with high frequency carrier wave. Got it? So note down. We will stop here for today. Okay. Bye.